Okay, finishing up classical population genetics. I'm not going as deeply into this as some. There's some topics that we just don't have time to cover and also hit everything else that I want to. But one of the things I want to hit before we take leave of all this math stuff is how you expand the Hardy-Weinberg equilibrium to more than uh, two alleles. All of the examples we've talked about so far, you only have two alleles whose frequencies are P and Q. You can use this basic idea to look at systems where there's more alleles than two. In fact, I think the off the bat, I remember hearing of at least one human gene that's got 26 alleles, and you can expand this to systems where there's any number of alleles that you want to. So look at question 11. It's about a gent named PDN Hebert or Herbert, or if he's from Louisiana, where I'm from, Hebert. And he studies the frequency of alleles for a gene in Daphnia. Daphnia is sometimes called the water flea. We use them in our 1400 class in a lab that we do. I don't remember if they use them in labs in 1440 or 1441, but these things are extremely common in freshwater ponds just about everywhere. We used to have a bunch of them in the greenhouse here at UCA. They're if you've ever kept a freshwater aquarium, you can buy freeze-dried Daphnia to feed to your fish. So anyway, they've got an enzyme that happens to be called malate dehydrogenase. And sneeze. Okay, sorry, sneeze stuck halfway out. Excuse me. Right. Back in, I think, the early 70s, a Harvard professor named Richard Lewontin invented this technique called gel electrophoresis. And that produced a whole lot more data for population geneticists because you could take a Daphnia, grind it up in a beaker, electrophorese its tissue fluid. And you've all done electrophoresis. You should know what this is. Stain the gel for a particular enzyme and read off the organism's genotype just by counting the number of bars that you see. And different alleles for this particular enzyme happen to migrate at different speeds through an electrophoresis gel. So there's three alleles of malate dehydrogenase, and they're abbreviated S, M, and F. That stands for slow, medium, and fast. And that just refers to how quickly those bands move away from the well on an electrophoresis gel. So when electrophoresis was invented, it suddenly made it possible to gather lots more data on alleles and allele frequencies and, plug that into population genetics. So Herbert, Hebert, whatever he is, found the following genotypes, which I very cleverly posted in the whiteboard in advance. So he has three that have the genotype SS, and 8 with the genotype SM, and 19 with the genotype SF, and so on. I won't read all of that, but there's a total of 114 Daphnia that he sampled. Okay, if there's 114 Daphnia, that means there's 228 alleles. Each Daphnia has two alleles. What are our allele frequencies? Well, we can call P the frequency of the slow allele, And how do we calculate that? Well, I'm sorry, I'm trying to wrangle these text boxes and things that you may not see. Okay, there we go. How do we calculate that? Well, think about it. It's a fraction. We have in the numerator, we have 3 Daphnia that have 2 alleles each that are S. And we have 8 Daphnia, the SM ones, that have 1 allele each. And we have another 19 that have 1 allele each. So that's going to be divided by 228, the total number of alleles in the population. And that is half a tick. Let me pull up my handy dandy calculating gizmo. That's going to be 14 divided by 228 equals, I make that out to be 0.144. Okay, right. We'll let Q be the frequency of the medium allele. And that is equal to, let's think this over. We have 15 MM individuals that have 2 of each allele, right? That's 15 times 2. And then we have 8 SMs that have 1. And then we have another 37, the MF individuals that have 1 allele each. Okay, so 15 MMs times 2 plus 8 SMs with 1 plus 37 MFs with 1, all divided by 228. And that should be equal to, let's see, that's equal to 75 over 228, which I make out to be 0.329. And then the frequency of the F allele we can call R if we want to. If you had lots of alleles, you'd use P sub 1, P sub 2, P sub 3, and so on. But we can, as far as I'm concerned, we can use P, Q, and R. So the frequency of the F allele is what? Well, we have 32 FF individuals. We have 32 FF individuals that have 2 alleles each. And we have 19 individuals with the SF genotype that have 1 allele each. And we have 37 individuals with the MF genotype that have 1 each. And we divide that all by the total number of alleles in the population. And that is 2 times 2 plus 19 times 1 plus 37 times 1. That's 120 divided by 228. And I get 0.526. Okay, quick check to see that I did my math right. Do these add up to 1? 4 and 6 is 19, 9, 5. They add up to 0.999, close enough. The missing 0.1% is going to be round off error. But they add up to very close to 1. So we did our math correctly. Okay, so that's our allele frequencies. How do we test whether the population's in Hardy-Weinberg? Well, let me go back to our imaginary ocean. Okay, there's our imaginary ocean, and there's our imaginary ocean floor. And on the bottom, we had a bunch of oysters, if you remember that we did this. I know we've gone from Daphnia to oysters, but bear with me for a sec. And remember how we got that Hardy-Weinberg relationship in the first place. We imagined that all these oysters fired off a bunch of eggs, not drawn to scale, and a bunch of sperm. And then we envision probabilities of picking eggs and sperm out of this pool. All right. So let's pretend for a moment that we have some of our eggs have genotype, are carrying the S allele, and some are carrying the M allele, and some are carrying the F allele. And the same for our sperm. Some of our sperm are carrying S, some of our sperm are carrying M, and some of our sperm are carrying F. And now imagine that we're just reaching in and picking out eggs and sperm of different genotypes. Okay, so we're back in our little gamete pool here. Okay, the probability of you picking out an egg that has the S allele and a sperm that has the S allele, that's equal to the probability of you picking out an S egg, which is P, times the probability of you reaching out in and picking out an S sperm, which is also P. So that's going to be P squared. The probability of reaching in and picking out an egg that's M and a sperm that's M is going to be Q, which is the probability of picking an M egg, times Q, which is the probability of picking out an M sperm, which is Q squared. And then the probability of you picking out an egg that's F and a sperm that's F is the probability of picking out an egg with F, which is R, times the probability of picking out a sperm that's F, which is also R, which is just equal to R squared. Okay, what's the probability that an egg sperm pairing will give you the genotype SM? Well, it's the probability of picking out an S egg, which is P, times the probability of picking out an M sperm, which is Q, or the probability of picking out an M egg, which is Q, times the probability of picking out an S sperm, which is P. So it's equal to 2PQ. And by the same reasoning, the probability of picking out an SF, getting an SF offspring is equal to 2PR. And the probability of picking out an MF offspring is equal to 2QR. Okay, so in any situation like this, the probability of getting any homozygote is the square of the frequency of that allele. So if I had 26 alleles listed allele A through allele Z, under Hardy-Weinberg, the probability of getting a ZZ individual would be equal to the frequency of, would be equal to Z squared. Okay, I set that up slightly wrong. If I have 26 alleles, the probability of an individual in that population being homozygous for allele number 26 is just the square of the frequency of that allele. Let's just do it that way. And then the probability of any heterozygote is 2 times the product of the frequencies of the 2 different alleles. So that's how we get this. That's how we can expand Hardy-Weinberg equilibrium to any number of alleles that we want to. So let's go ahead and work the problem once I get this erased. Okay, I didn't mean to erase all of that. Looks like I did it anyway. Okay, great. So how do we test whether the population is in Hardy-Weinberg equilibrium? Well, let's go ahead and do one of these observed versus expected tables. Make sure I've got enough room right there. Okay, what's our observed frequency of SS? Well, it is equal to, we have 3 individuals out of 114. And 3 divided by 114 is 0.0263. Okay, our observed frequency is 2.6%. What's our expected if the population's in Hardy-Weinberg? Well, it's p squared, which is 0.144 times 0.144, which is equal to 0.0207. 0.0207. Okay, SM, our observed frequency is 8 over 114, which is equal to 0.0702. 0702. Our expected frequency is 2PQ, which is 2 times 0.144 times 0.329, which is 2 times 0.144 times 0.329 equals 0.0948. 0.0948. I probably should have worked this problem in advance because the calculation part is probably about as interesting as watching paint dry. But the frequency of SF that we observe is 19 over 114, which is 0.167. Okay, the frequency of MM individuals that we observe is 15 over 114, which is 0.132. And the frequency of MFs that we observe is, hey, sweetie, equals 37 over 114 is 0.325. And the frequency of FF individuals is 32 divided by 114, which is 0.281. Okay, so that's all of our observes. And our expecteds are just going to be, the expected SF is 2P. Okay, here we go. Sorry, late comer there. Is 2PR. Sorry, I'm all right. Sorry, momentary annoyance right there. And 2PR is 2 times 0.144 times 0.526, which is equal to some number or other. 2 times 0.144 times 0.526 equals 0.151. The frequency, the expected frequency of MMs is going to be Q squared, which is 0.329 times 0.329. And that is 0.329 times 0.3329, 0.108. The frequency of the MFs is 2QR, which is going to be 2 times 0.329 times 0.526. That can't be right. Times Wagner times 0.526, which is going to be 0.346. And the frequency of the FFs is going to be R squared, which is 0.526 times 0.526, which is 0.277. Okay, blah. All right, that was not the most scintillating moments of lecture that I've ever had. But now you've got your observed genotype frequencies. That's calculated directly from the data that you're given. And your expecteds are right here. And it's a little hard to say just whether we're in Hardy-Weinberg or not just by looking. This would be yet another case where you'd want to plug that into probably a chi-square, run a test on that. But that's basically how you do the problem. And that's how you expand to more than just 2 alleles. Okay, hope that didn't put everybody to sleep. Real quick, I'm going to show you one, and I'm not going to work the whole thing, but this kind of freaks people out sometime when they see a 4 allele problem like this. This is number 12. Francisco Ayala sampled a population of deep sea starfish, and they used gel electrophoresis to determine various allele frequencies. And they looked at one gene, happened to be for an enzyme called tetrazolium oxidase, and it had 4 alleles, and they're called TO100, TO107, TO114, and TO120. And they found that the frequency of each allele was as follows, was those numbers right there. And they observed that 70.6% of the population was heterozygous. And the question is, does this match what we'd predict for a population in Hardy-Weinberg? This is not nearly as hard as it looks. And how you would solve it goes like this. Let's clear this whiteboard. Let's clear everything out. And we have this data right there. And we also know that 70.6% of these starfish are heterozygous. Okay, how the heck do we solve this? Well, remember that the expected frequency of any homozygote in Hardy-Weinberg equilibrium is equal to the square of that homozygote's allele frequency. Okay, so if you want to know the total number of all homozygotes in a population, we could abbreviate that if you wanted to as HO. That's the frequency of homozygotes. What that is equal to is simply the sum, right? Remember using sigmas for a sum. Of the squares of the allele frequencies. So if we have alleles, if we have allele frequencies P1, P2, okay, I can't do subscript. You know what? I'm gonna write this since I can't type it. Okay, so we have a sum for however many there we go. That worked better than trying to type all of that. Okay, remember how sigma notation works. If we have however many alleles of a particular gene, we can call them P1, P2, P3, P4, dot, 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 you know, all the way to Pn. We'll let lowercase n be equal to the number of alleles that we have. And this just says, take each allele from 1 to n, square the allele frequency, and add all of those allele frequencies together, and that gives you the total number of homozygotes in the population. So if we have 4 alleles, these frequencies we can call P1, P2, P3, and P4. The total number of homozygotes is just going to be the sum of the squares. So if we sum the squares of all of these, I'm not even going to type all of this, but that is just equal to 0.206 times 0.206 plus 0.147 times 0.147 plus 0.353 times 0.353 plus 0.294 times 0.294.
Typing.
Sorry?
I don't think it was typing.
Okay, well, I'm typing this off the share.
Oh, okay. I can't see it. I'm sorry.
Okay, yeah, I'm not expecting you to. I've been doing all these calculations on a window that I'm not sharing with you folks.
Oh, okay.
But you can certainly follow along. So what I get is 0.206 times 0.206 plus 0.147 times 0.147 plus 303 times 0.294 times 0.294 equals what I get is 0.275. So if this population of deep sea starfish is in Hardy-Weinberg, we would expect the frequency of homozygotes to be 0.275. Well, what's the frequency of heterozygotes? You could calculate it as okay, if we let these four be P, Q, R, and S, you could calculate 2PQ plus 2PR plus 2PS plus 2QR plus 2QS plus 2RS. And that's the long and painful way. But since every starfish has to be either a homozygote or a heterozygote, there's no other option. The frequency of heterozygotes just has to be 1 minus the frequency of homozygotes. So it's equal to 1 minus 0.275, which equals 0.725. So the expected frequency, if we're in Hardy-Weinberg, is 0.725. The actual frequency of homozygotes is 0.706 or 70.6%. So that's our expected if we're in Hardy-Weinberg. That's our observed. That's not enough to do a chi-square test on. Going further than that would require access to some raw data that I didn't happen to have when writing the question, but that's basically how you solve questions like that. If you have lots of alleles, then the frequency of all homozygotes is just equal to the sum of the squares of all of the allele frequencies. So problems like that one, problems like that one right there shouldn't freak you out. That's how you solve those. Okay, you guys want to take a bit of a break before I start going on about inbreeding? Okay, I'll take that as an enthusiastic yes. Okay, all right, always good to see the thumbs up there. I've got 9:42. Let's not take 18 minutes. Let's come back here at 10:55 and we'll resume this and I'll talk a bit about inbreeding. All right, so I'm going to go ahead and stop recording.